morning. I am Alberto Scolari. I am a master student at Politecnico di Milano. I am currently working on the FASTER project.
Hello, I'm Fabrizio Spada. I'm working on a FASTER research project. We've been joint collaboration between ST Microelectronics and Politecnico di Milano, in particular Next Laboratory.
Within the FASTER project, we are working on the SPIA development platform provided by ST Microelectronics. The goal of our work is to port the ray tracing algorithm to this board. In particular, what we want to do is to port part of the computation to an FPGA accelerator. Our platform is composed of two parts. The main part is the SPIA board. Here you see a SPIA 900 board, while the other part is an FPGA, in particular a Virtex 5 by Xilinx. The STM SPIA board, it is equipped with a dual-core Cortex-A9 processor, 1 GB of RAM memory, and 2 flash memory, a NOR memory of 8.5 MB and a NAND memory of 256 MB. About the software equipment shipped with this platform, we have a Linux 2.6.37 operating system and a file system providing all the needed tools to run a full system. Let me present you how the ray tracing algorithm overall works. Well, this algorithm basically shoots rays from the camera point of view to each pixel of the image. By following the direction of these rays, it looks for the intersection of each ray with the objects of the scene. If it finds an intersection, the algorithm computes the color contribution on that specific pixel where the intersection is placed, and then computes also the reflecting and refracting rays that depart from the original ray. In turn, these new rays are shot against the other objects, and the process is repeated again and again up to a certain level.
Here there is a PC that is connected to SPIA board via SSH interface. We also developed a graphical interface in order to show the image rendered in software and in hardware. So the steps are: first, download the RayTracer application on the SPIA board, then connect via SSH. Now we select if render sphere, ring or triangle, then click render software. Now we can see that RayTracer application, ST RayTracer, the first line, computes RayTracer algorithm. Now I want to display image, so click display image and we can see the results. The system architecture implemented on FPGA in order to port some part of the ray tracing algorithm. There is a custom domain engine that is connecting to the cores, intersect sphere, ring and triangle. There is a demultiplexer and multiplexer in order to select at runtime the data flow of the application. In the cores there are queues that are mapped on Axie4 stream interface.
To expose to the software layer and to the application the computational resources on the FPGA, we developed a kernel driver for Linux. This driver creates two device files inside the dev directory. One device file shows a DMA coherent buffer that is used by the application and by the FPGA for the data communication. This buffer simply stores the data that must go to the FPGA and the data that from the FPGA must go to the application. The other device file instead exposes the DMA interface that we developed custom on the FPGA among the various IP we designed and deployed on the FPGA. Using two different files lets the user, for example, write the buffer multiple times and send a whole chunk of data in just one transmission. So potentially increasing the bus transfer rate. In particular, in this figure, we see the flow of data of the restructured application. The application has been restructured to leverage hardware acceleration by sending data to the FPGA cores. Here, the flow is a synchronous flow and is the current implementation of the application. In particular, the application issues a write call to the buffer. This write calls falls back to the kernel driver that copies the memory from user space to the DMA buffer. Then the application triggers the transfer on the bus to the FPGA, waits for the completion of the computation on the FPGA, and gathers the data back through the same path in the other direction. So from FPGA to DMA buffer, from DMA buffer to finally the user space buffer. This synchronous flow now happens for each ray, and thus is subject to future optimizations to increase the hardware parallelism we can exploit.
Now render hardware. So look at the PC. Now we have a flag -R that forces the hardware execution of intersection of ring. So, and we get the final result, display image, ring.
To further improve the performance of the demonstrator, we can draw some guidelines to identify some modifications both in hardware and in software. In hardware, in particular, we have to face the latency of the current bus. So ideally, we should deploy on the hardware a more performing bus in order to decrease its slowdown and increase its transfer rate. In software, instead, the main challenge is to move from the synchronous model I showed before to, as much as possible, asynchronous model, so that the computation on the FPGA and that in software can ideally proceed in parallel. In particular, the software component should compute input data and buffer them up to a certain point when, in large chunks, they should be sent to the FPGA. But while this transmission is in progress, it is fundamental that the software component goes on with its computation.